In this video, we'll prove that the ordering on the rationals is transitive. This is one of the axioms of ordered fields that you would need to verify in order to show that the rationals is in fact an ordered field. So let's recall our definitions of the rationals. If we have an integer m and a natural number n, then we define the rational number m over n as the set of all fractions that are equivalent to the fraction m over n. And of course, Q is the set of all rationals. Okay? Equivalence of fractions is defined in terms of cross multiplication. So MQ equals NP if and only if the two fractions are equivalent. And so that allows us to define what it means for two fractions, two rational numbers to be equal. So two rational numbers are equal if and only if MQ equals NP. Okay? So if MQ equals NP, then the infinitely large set of fractions that are equivalent to the fraction m over n is the same set as the infinitely large set of fractions that are equivalent to the fraction p over q. So that's equality in the rational numbers. Okay, and let's define again the order on the rationals. So if we have two rational numbers f1 and f2, and if we represent f1 as m over n, and if we represent f2 as p over q, then f1 less than f2 means that m times q equals n times p as integers. So that's how we define the ordering on the rationals in terms of the ordering on the integers. So the result that we're going to prove is that the order on the rational numbers is transitive. So let's start with three rational numbers, a, b, and c. Let's assume that a is less than b, and let's assume that b is less than c. Then of course, to prove that the ordering is transitive, we have to show that a is less than c. Alright, so to get started doing that, let's write a as the rational number n over m, b as the rational number p over q, and c is the rational number s over t. So in particular, all of the numerators, n, p, and s, are integers, and all of the denominators, m, q, and t, are natural numbers. So our first assumption, a less than b, implies that, according to our definition of the order, n times q is less than m times p, and our assumption that b is less than c, according to our definition of the ordering on the rationals, means that p times t is less than q times s. Okay. Now notice that if we take the first inequality there, nq less than mp, and we multiply that by t, it preserves the order because we're multiplying by a positive number. So since t is a natural number, it's positive. So since nq is less than mp, we also get that nqt is less than mpt. Alright, so let's now take our inequality pt less than qs and multiply it by m. So if we take pt is less than qs, the inequality we got from the assumption that b is less than c, we can multiply that by m, which again is positive, it's a natural number, so multiplication preserves order in this case. So we get mpt is less than mqs. And of course now we have both nqt is less than mpt, and we have mpt is less than mqs. Alright, so we can use transitivity of the ordering on the integers to conclude that n times q times t is less than m times q times s. Okay, notice that both the terms in that final inequality there have a q in it. Now q is positive, so we can apply the cancellation property to get nt is less than ms. Alright, so we canceled that positive number q from both sides of the inequality there, and we get that nt is less than ns. Notice that n is the numerator of a, t is the denominator of c, m is the denominator of a, and s is the numerator of c. So that's exactly the definition of n over m less than s over t. Okay, and since a was represented as n over m and c was represented as s over t, we have a is less than c. And that's exactly what we needed to prove to show that the ordering on the rationals is transitive. That's it for this video. Thanks for listening.